In today's lesson, we will be looking at anti-differentiation by parts, otherwise known as integration by parts. Integration by parts is the most complex method of integrating, and it is used for any integrals that are, as this says, too complicated for basic rules or for substitution. So substitution that we did in the previous video was used for composition of functions, which would be more akin to the chain rule for derivatives. This will be the product rule. So it is very, very similar to the product rule, and the formula actually comes from the product rule. So if we look down at the actual formula for this, we have the integral of u dv equals uv minus integral v du. So this comes directly from the product rule that we had for derivatives. So for the derivative of a product, we'll go again with uv. It was u dv plus v du. That was the product rule. First times the derivative of the second plus second times the derivative of the first. So if we were to undo all of this with antidifferentiation, the derivative and the antiderivative here on the left-hand side, those would go away, and on that side we get uv equals the integral of u dv plus the integral of v du. So we now have all of the same parts that they have in this formula. We would just need to do a little bit of rearranging by taking this integral of v du and subtracting it to the other side. We would end up with uv minus the integral of v du equals integral u dv. So it's the exact same formula that they've given us, just on opposite sides of the equation. So that's where this formula comes from. It is directly from the product rule of derivatives. So we will be looking at functions that are products. So anytime we see two functions that are not related, that are multiplied together, we should start thinking about the integration by parts formula. So we'll talk about how to kind of identify the pieces next. There's a really easy rule for this, and it is LIATE, liate, or if you take Latin, liate. And this is the order for selecting u. So you always want to go through this order when you're picking your u. The other part will then be the dv. So we start with L, logs. I is for inverse trig functions. A is an algebraic function. Now this is the most kind of open-ended of them. Logs, anything that says log or ln, that's a log. Inverse trig is any trig function to the negative first power. Algebraic function can be any function, like a power rule, x squared power function, polynomial pieces. It can be a constant function, can qualify as an algebraic function, so there's a lot of flexibility on the algebraic. T-trig, that's pretty self-explanatory, and then exponential function like e to any power, e to the x, whatever it might be, e to the u. So those are the ways that we go through selecting u. So whichever one of those comes first, that is going to be the u, and then the other part will be dv. Since e, exponential functions, is last, that one will always have to be the dv. So if you ever see an exponential part, that is always going to be dv. Okay, so we want to reference that, LIATE, as we go through each of these problems. And again, these are the most challenging of the anti-differentiation problems that we will have. So it might take some time for this to sink in, but that's okay. There are several examples here of possible different setups, and we'll go through each of them. And the first thing to do would be to select your u, which is right here, and your dv. I always set up my problems like this. As soon as I recognize that it's multiplication and not a composition that would use a u substitution, I go ahead and set up this set of 4 pieces of information so I can fill all of that out. So again, we want to go back through LIATE. There is no logarithm in this problem. We do have a trig function, but it is not inverse, so no L, no I. A, algebraic, that is our x function. So that is an algebraic function, so that becomes our u, which means the trig function, t, is our dv. So where we want to go from here, we want to take the derivative of u and the antiderivative of dv. Now, if you pick a u that you do not know the derivative of, chances are you've picked the wrong u. If you pick a dv that you do not know the antiderivative of, again, chances are you've picked the wrong dv. These should be known derivatives and integrals. If they are not, go back and try again. So the derivative of x is 1 dx. Just like the substitution, it is very important that we write out that dx. And we really should have the dx here with the sine x, so we can take that antiderivative with respect to x. So the dx does matter here. The antiderivative of sine, that would be negative cosine. Okay, so now we have all of our parts. We can now plug this into the integration by parts formula, uv minus v du. We'll still have another piece to antiderive, but now it should be a known antiderivative. So again, the formula is uv, so our u is x, times v, which is negative cosine. Very important to put that negative cosine in parentheses so we don't get confused, maybe x minus cosine, that's not what we want. So we have uv minus the integral of v, so that same negative cosine again, du, which is dx. Again, it's very important to write the dx wherever it belongs so we can actually have this integral and it works and it's telling us what to antiderive. Now this is just a quantity. We put that together, it's negative x cosine x, nothing to do really there. And then inside this antiderivative, that is a known antiderivative, that's a known integral, we can do that. What I would always suggest, and this problem it's not too terrible, but I would always suggest any constants or negatives that are inside the integral come out before you take the integral. We'll see a couple examples where there are fractions and whatnot, so I would always pull that out first and then take the antiderivative. So that's going to change to a plus sign, and then the antiderivative of cosine is sine. And there we go. We always want to add our plus c since we're doing a general antiderivative, but we have negative x cosine x plus sine x plus c. That is our antiderivative of x sine x. So the biggest part is getting the setup. Once you've got the setup, the rest of the work should be pretty straightforward for the first sort of several examples of this. They do get more complicated than this, but for the initial problems, it's really a lot of setup work and then an easy antiderivative. Okay, so our next example here is integral of 2x squared ex dx. Take a moment and write down what you believe u and dv are, and then go ahead and find du and v. Okay, hopefully you found what u and dv are. So again, we go through our liate, liate. As I mentioned when I went through that, e is last. So anytime we have an exponential function, that will always, always, always be dv. So I know right away that that is dv. And then this u is 2x squared. We'll see in just a moment here, this red example off to the side, what that really, why that e to the x and why the trig functions are the last two functions on the page. Okay, so now we have our u and dv, so we're ready to find du, so take the derivative. That's an easy one, 4x dx. I will constantly forget to write my dx in the original setup, but that's okay, as long as we go back and realize it. Then the antiderivative of e to the x, that's an easy one, it's e to the x. Now we're ready to plug into our integration by parts formula. So we have uv, so 2x squared, ex, minus the integral of v, ex, du, 4x dx. So we are now ready to evaluate that integral. Hopefully you notice we still have a product in that integral. So we really didn't change the form of the original problem. The original problem was an algebraic function times an exponential function. In this new integral, we have an algebraic function times an exponential function. So we really haven't gotten to a point where we can take a standard antiderivative, which means we get to do this whole process again. So this is repeated use of integration by parts. And we are going to do the exact same process for this part of the integral here. We recognize that that's still there. We push it off to the side. It needs to come back in our answer, but we don't need to do any more work with that because there is no more antiderivative there. So we do the same setup again. Don't get confused. This is a different u. If you want to use like u sub 1, v sub 1, whatever that might be, go for it. I'm pretty comfortable using the u again. Just don't get confused. So u has to be the algebraic function again. dv has to be e to the x again. So v is e to the x, and du is 4 dx. Now I know that I said in the last problem to go ahead and factor out that 4 to start. You can. It's going to be distributed at some point to different things, so leave it in, take it out. It shouldn't change the problem as long as you're careful with your algebra. For this repeated use, I went ahead and left it in. So I'm going to go ahead and recopy that 2x squared so I don't forget about it. Minus, and then this is an important piece of notation, I guess, to make sure you get the correct signs for your answer. It's minus this integral, which is going to be minus this entire piece of the integration by parts formula. So whenever I do repeated use, I always put a giant bracket there so I know that I need to distribute that negative at the end. Okay, so now we're ready to use the integration by parts formula. Again, it's uv, so 4x ex minus the integral of v ex du, which is 4 dx. Now would be a great time to bring that 4 out front of that antiderivative. So I will do that, rewrite this line completely. You don't have to do this step. If you're confident in taking that integral as is, save yourself a line of writing, that's fine. 4x ex minus, bring that 4 out front, integral ex dx. At this point, we've taken the antiderivative of e to the x twice, and it has not changed. So that's the last step that we need to do here, is take the antiderivative of e to the x. So again, I'm going to rewrite everything. We have 2x squared ex minus, still using my bracket, 4x ex minus 4. The antiderivative of e to the x is still e to the x. Okay, so that is an acceptable answer. If you want to clean it up a little bit, you can. I would not go as far as like factoring out. I know that they all are divisible by 2 and they all have an e to the x in them, but I wouldn't waste any time factoring that out. I would just finish by removing the brackets and parentheses and distributing that negative to the other two parts. So negative 4 e to the x, 4x e to the x, excuse me, plus 4 e to the x. And I would stop right there. That's good enough for us. If you're inclined to do so, go ahead and factor if you want, but again, it doesn't get you any bonus points, so I would stop right there. Okay, so if we have repeated integration by parts like this, there's actually a faster method that we can use. This works best when you have AE, so algebraic and exponential, or AT, I'm not going to show you that one, but that algebraic and the trig function. So the reason why we have to do repeated use of integration by parts when we have an exponential function or a trig function is because their derivatives and integrals are cyclic. So if we derive e to the x, we are never going to get rid of the e to the x term. It'll always be in there, potentially with something else. If it was ex squared, it's e to the u du, so you're going to have other parts, but you'll always have an e to the x part in there. You will never derive the e to the x out of the problem. Same thing with sine and cosine. So if we take the derivative of sine, it is cosine. If we take the derivative of that, it's negative sine, and then negative cosine, and then back to positive sine. So that's cycles. So any derivative that is cyclic, you can use this tabular integration for, provided your other function is algebraic, because the algebraic function will always derive to 0. X squared, if you do 2 or 3 derivatives there, you're going to get constants and then 0. So that's the setup we're looking for. If we have AT or AE, we can use what's called tabular integration. So tabular integration is a lot quicker than doing repeated use, especially when you have a bigger power of x as your algebraic function. If we look at the problem we just did, we did repeated use of integration by parts twice, and it is no coincidence that the power on x was a 2. That's how many times we need to do it until we get a piece of the algebraic function that is a constant that lets us take just the antiderivative of v to the x. So here, take a second and guess, yeah, we're going to have to do it 4 times, 4 uses of integration by parts formula. That is about 3 too many times for me. So if we use this tabular integration, if we recognize this problem as a problem that we can do it on, we're going to save ourselves a lot of time and effort. Yep, so here's what tabular integration looks like. Tabular, you make a table, hence the name tabular. On the left column, you're going to be putting in your u function, what would have been your u, and on the right column, it would be dv. For the left-hand column, you're going to be taking derivatives the whole time, because that's what we did with u. We found du, and then du again and again. For the right-hand column, the dv side, you're going to be taking integrals. And that's because we had dv, and then we found v. So it still fits the same pattern of work we were doing. So our original u is x to the 4th, and our original dv is e to the x. So now we can go through one side at a time and take all of the derivatives until we get 0, and then take a corresponding number of antiderivatives on the other side. This one is really straightforward with the e to the x because there's no constant in there. Not, an e to the x, e to the 2x would have a constant coming out through it. Sine of 8x, there would be a constant coming out through that. So there is a little bit more to do with those. We're not seeing that right now. So I might be able to throw another example in here that has that. Let's go ahead. I'm going to go ahead and change this to e to the 2x, just to make it a little bit more interesting with that. Okay, so the derivative of x to the 4th is 4x cubed, and then 12x squared, and then 24x, and then 24, and then 0 would be the final one. Okay, so we've got those derivatives on the left-hand side. Now for the integral, since it's e to the 2x, the antiderivative is still going to be e to the 2x, but now we need to divide by the derivative of the upper limit. Okay, so if we think about taking the derivative of e to the 2x, it would be e to the u du. Okay, so that would be e to the 2x still times the derivative of the power. The derivative of 2x is 2. That is derivative. So if we take the antiderivative, we would be dividing by the power's derivative, so dividing by 2. So hopefully that makes enough sense to you. Anytime that there is a multiple on the inside, if it's a composition like this, we're going to be dividing by that number. So this is dividing by 2. And we will keep dividing by an additional 2 every time we take the integral. So the next integral would be e to the 2x divided by now 4. We're multiplying that denominator by 2 every time. We're putting another 2 on the bottom. So the next one would be 2x all over 8, and then e to the 2x over 16, and then e to the 2x all over 32. So we have all of these parts now. We did our derivatives on the left, our antiderivatives on the right. Now we are ready to combine these and write out our antiderivative. So the way we do this is we go diagonally. So that x to the 4th will go with the e to the 2x over 2. The cubed, the squared, that, and that. 0 doesn't have anybody to combine with, because if we did that, it would just be 0. 0 times anything is 0. So we don't need to use that one. This first dv will not ever be used. If you notice the or the integration by parts formula, there is no dv anywhere on this right side of the equation. So dv does not come back to play. Okay, so now we need to rewrite this. One last little caveat is the sign of these alternates. So the first SIGN is positive, the next is negative, positive, negative, positive. And if we look at the problem we just did, we will notice that, first of all, I forgot my plus C. Second, the sign of the first term is positive, second term is negative, third term is positive. So the signs SIGNS alternate when you're doing this repeated integration by parts or when you're doing tabular. First term is x to the fourth e to the 2x over 2. The next term is minus 4x cubed e to the 2x over 4 plus 12x squared e to the 2x over 8 plus, oh no, minus, we're alternating, minus 24x e to the 2x over 16, and the last one should be plus 24, no x, e to the 2x over 32, and then I'm not going to forget my plus c this time. So there we go. We have the integration completed. That would have been a headache to do with repeated use of integration by parts. So anytime you have an AT or AE setup, you can use this tabular integration. So the last example here is probably the most challenging and the most frustrating and kind of the weirdest one in my opinion. I really don't like this solving for what's called the unknown integral. So this happens when you have two cyclic functions. So we have t and e here. We have sine, which is a trig function, and e to the x, which is an exponential function. So when we do this integration by parts, since they're both cyclic, the derivative is never going to go to 0. The antiderivative is always going to stay in e to the x. We're never going to get rid of anything. And if you do repeated use of integration by parts, you'll do it forever. If you do tabular integration, you'll keep going forever. So we have to recognize what's going on here to be able to actually finish this problem. And to me, it feels like a very cheap solution. We do a few steps and then we say, okay, and then we do a little bit of hand waving, a little bit of algebra, and then it's over. I don't really like these. That's the process. That's what you have to do. So we'll take a look at it. We still want to use our LIATE rule. So that means trig comes first. So sine is our u. And e to the x is our dv. So the derivative of sine is cosine. And the antiderivative, we've done this several times now, is still e to the x. So we'll do our integration by parts. We have uv. So I'm going to write the e to the x sine x. I just don't like having sine x and then e to the x because it gets confusing about what's where and parentheses and all that. So e to the x sine x minus the integral of v du. So again, we've not really changed the form of the original problem. It's still a TE problem, so we would need to do integration by parts again with these new pieces. So the new u will be the trig function, so cosine. The new dv will be, again, e to the x dx. V is e to the x. And du, we've already done this one, is negative sine of x dx. Okay. So we have e to the x sine x minus big bracket uv, and I did what I said I wasn't going to do. We'll write e first, so we have this minus the integral of v du. Okay. So I'm going to go ahead and just move that negative outside. I don't like having that negative in there. It feels weird. You don't want to forget and accidentally do subtraction. So I'm going to erase all that, make that a multiply, and this becomes, that negative comes out to make that positive. Okay, so I'm actually going to go ahead and do this distribution now. And to save space, because there's another example down here, I'm going to start erasing some stuff. So just watch. The distribution turns that piece into a negative and this piece into a negative as well. Okay, we would be okay doing the integration by parts again. But if we do the integration by parts again, we're not going to get anywhere. We're going to be back to where we started because this is the exact same as the original problem. So after 2 steps, we need to recognize that. We need to take a second and go, wait a second, I've got the same thing that I started with. So this is the part where we get into some hand waving, and it is, in my opinion, kind of a weird solution, a solution that doesn't feel like we're actually doing calculus. It just feels like we are recognizing that, hey, this is a really challenging derivative, and we can't do anything else with it, and kind of throwing in the towel. So what we do here is we set it equal to the antiderivative that we started with. So we set it equal to this. And then we add this antiderivative to the other side since they are the same. So we'll have e sine x minus ex cosine x equals 2 integral ex sine x. So we've not really gotten rid of that integral, we've just combined it on the other side with what it is. So we now have that ex sine x minus ex cosine x is 2 of those integrals, which doesn't feel like we've done proper calculus. The last step is algebra. We just divide both sides by 2 to conclude that the integral of ex sine x dx is 1/2 ex sine x minus ex cosine x. And that's it. That's all we can do on that. We do the antiderivative antidifferentiation by parts twice. We recognize, hey, this is cyclic. They are never going to go away. We're always going to have an e and a trig function. So we have to do a little bit of hand waving, a little bit of not throwing in the towel, but just realizing that, hey, we're going to get stuck if we keep doing this forever. Figure out an alternate solution, and that's it. We algebra to the other side, divide by 2, and we are finished. Kind of weird solution in my book. I'm not the biggest fan of these, but this does happen. So if you go through these problems and look for certain things, you're going to have a much better idea of where to start. So if you have an A and T or an A and E, that's great. We can do tabular. That's the fast one. That's a good setup. If we have other stuff, if we have Li, we can do that. La, we can do that. It, we can do that. That one's kind of weird when you have an inverse next to a trig function. Any of those other combinations can potentially work, but if you have an AT, it's always, always, always going to be the unknown integral because neither of them will derive away to a 0. So always check for AT, that's the unknown integral. You'll do, TE. You'll do integration by parts exactly twice. You will set it equal to the original equation, the original integral. You will combine the like terms to the other side, and then you will divide by whatever constant you have. If we had some constants in there, like e to the 2x sine of 5x, it would make our answers have some more fractions in them. We'd have a different number other than 2 on the other side, so it's not always 2, it's not just divided by 2. We do need to make sure those constants work out, like the tabular integration problem where we had those building constants, 2, 4, 8, 16, 32. That same kind of thing will happen if you have constants in the unknown integral problem. Okay, so the last problem is kind of fun. If we look at this, this is the antiderivative of the natural log. We've seen the derivative of the natural log. We know that. All right. If we look at this, there's no multiplication. It's one function by itself. We can actually use integration by parts on this. So this, in my opinion, is one of the more elegant uses of integration by parts. It's one of the more subtle uses. You have to sort of understand that, okay, I don't know this antiderivative. There's not there's no list of this. There is in the back of the book, but there's no list of this that we've seen in the front of the text. How do I do this? Integration by parts is always a good option. Integration by parts always works. You can use it to integrate 2x. We just know how to do that with a much easier rule. So integration by parts always works. And for problems like this, it is the only thing that works. So what we have to do here is we have to, again, go through LIATE. So L, logs, we definitely have a log. We have the natural log of x. So that is our u. 100% for sure, natural log of x. So what does that leave for dv? The only other thing in this problem is dx. dx is an algebraic function. It is technically 1, which is a constant, which is a 0-powered x. So that is our algebraic function. So we actually have LA in this problem. So take a second, find du. We do know the derivative of natural log, so that's why it has to be our u. The whole problem is we don't know the antiderivative, so it cannot be dv. Okay, hopefully you've taken a second, done that. Pause the video if you needed to. The antiderivative of dx is x, and the derivative of natural log is 1 over x. So again, if you want to pause the video and try to write this through the anti-differentiation by parts formula, do that now. Okay, hopefully your setup looks like this. We have u, which is natural log of x, v. I'm going to write that before, so it's not ln x. I'll write it as x ln x, just so it looks a little bit better. So we have uv minus the integral of v, which is x, du, and I've, again, forgotten my dx on the du portion. There we go. So we have x 1 over x dx. Now, a cool thing happens on the inside of this antiderivative because we would have, power rule. We can still do it. We've got x times, so maybe an integration by parts again. X times 1 over x just becomes 1. So we have 1 dx. And that is a super easy antiderivative. We've already done that. We literally did that in the first step of the problem. So the antiderivative of 1 dx is x. So we get ln x minus x. So that's a really, in my opinion, elegant solution for an antiderivative that we don't know. That's not a standard antiderivative. This method also works for the antiderivative of like the inverse tangent. That's a fun one. So the antiderivative of inverse tangent. We know the derivative of the inverses, even just the antiderivative of sine inverse and cosine inverse. We know the derivative of those, but we don't know the antiderivative of those. So those can be done using this formula, this anti-differentiation by parts formula. Whatever function they give us, we call that the u, and then our dv is just dx. We consider dx the algebraic function, and we work from there. So those are some fun examples. There might be a few problems like that in the book, so I would encourage, if it's not part of the homework, to try that. Otherwise, this, again, is the most challenging of the anti-differentiation processes, so this might take some time to get good at. I would suggest working through problems and then coming back to the video to find something similar or checking other resources because this does take a while to master, and there are much more difficult problems that we are not looking at today with different constants, with fractions, like I've mentioned a few times. So I would definitely suggest using your resources, practicing as many examples of these as you can, because it does take practice to master.